Let us discuss now Riemann's rearrangement theorem. This one is an interesting theorem because if you remember from a previous video, we saw that whenever a series, a real series, would converge conditionally, rearranging the terms could be interesting, could give unexpected consequences. Okay, and what Riemann realized was that the problem was that for a conditionally convergent series, we have actually two divergent series involved, one with the positive terms and one with the negative terms. So that's, I split the theorem in two parts. The first one just says that both the sum of the positive terms and the sum of the negative terms are divergent series. And then the second part, that is the important thing, says that for any given real number you pick, there exists some rearrangement an prime such that the sum of the rearrangement, the rearranged series, is going to converge to the original number you gave me. So let's start with the proof of part one. Here, the first thing we need to notice, let's call that step one. Okay, here we notice that a conditionally convergent series must have positive and negative terms. Conditionally convergent implies the series has positive and negative terms. Let me move this over here. Okay, this is easy to prove because if all terms were positive or all terms were negative, then the series will be absolutely convergent. Okay, write down the details. So step two, in fact, if a series is conditionally convergent, then it must have an infinite number of positive and negative terms. Okay, so it cannot be that only the first 10 are negative and then everything else is positive. Okay, to show this is again very easy. Just notice that if the series has only a finite number of negative terms, for example, then the remaining series of positive terms, it must converge. Okay, since we know that only a few of them are negative, but then that is equivalent to saying that the tail of the series is an absolutely convergent series, which is against the assumption that the series was conditionally convergent. Okay. In other words, if we have a finite number of negative numbers, we can put them aside, and whatever is left would be an absolutely convergent series, which cannot be. And now, once we know this, we can actually go into the main part of the proof. Here, what we are going to do, we are going to write the series into the sum of two. Okay, and here this Pn and Qn are two series that have all the positive terms, P for positive, and Q all the negative terms. Okay, so how do we write this? What we want to also do is to keep track of where in the sequence, where in the series its term appears. Okay, so in order to keep track of that, we are going to define Pn, okay, as the absolute value of an plus an divided by 2, and Qn is the difference, absolute value of an minus an divided by 2. And we do this because if we compute what we have here, Pn is going to be an whenever an is positive, and it's going to be 0 whenever it is non-positive. Okay, and on the other hand, Qn is going to be 0 if an is positive, well, actually non-negative, and it's going to be equal to an if an is negative. Okay, so once it's written in this way, now you see what I meant, right? What we are doing effectively here is whenever we see some negative term, we just replace it by a 0, okay, and that produces Pn. And in the case of Qn, whenever we have a positive term, we just make it 0. And in this way, we keep track of the positive terms in the series, but also the moment, the index in the series where they appear, okay, the value of n. Okay, this is important because in this way we don't have to rearrange terms of the series, and the proof is less messy. Okay, so anyhow, let me very quickly emphasize with an example. Let's say 1 minus 1/2 minus 1/3 plus 1/4 minus 1/5 plus 1/6 plus 1/7. Okay, let's keep this with a minus. Here we go. So in this case, the sum of Pn is going to be 1 plus 0 plus 0 plus 1/4 plus 0 plus 0 plus 1/7, and so on, you see? And the sum of the Qn is going to be 0 minus 1/2 minus 1/3 plus 0 minus 1/5 minus 1/6 plus 0, and so on. And now it's clear. This example is just to make it super clear. When I add together the two series, right, I get back the original one. Okay, and you see what I meant, that adding those zeros in between doesn't change the value of the series, the sum, but it allows to keep track of where were the original negative terms or the original positive terms. Okay, this will be the sum of an. And this is, again, this is an example. It's not, properly speaking, this is not part of the proof. So let's put it with a parenthesis. Now, there are 4 cases, okay? Here notice that we have said that the sum is the sum of an is the sum of Pn plus the sum of the Qn. So there are 4 cases. So the first case, well, let me write all of them, 2, 3, and 4. So the first one is that the sum of the Pn, well, actually both converge. Okay. The second one is that the sum of the Pn converges and the sum of the Qn diverges. Then the sum of the Pn diverges, the sum of the Qn converges. These two actually are very similar. It's basically the same case. And then the last one is that both of them diverge, which is what we want to prove. Okay. So here, let's note this is what we want. Therefore, the cases 1 through 3, those cannot be. So we need to show that we get a contradiction in all those cases. Now, so we can have case 1. How do we show that? Well, because in that case, the sum of the AN, which is the sum of the PN plus the QN, okay? If both of them converge, then what I can do is to write the sum of the absolute values of the AN as the sum of the positive, those don't change, minus the sum of the negative. Okay? This is the equivalent of taking the absolute value of the negative ones. We can write this down as the sum of Pn plus the sum of the absolute value of the Qn. Okay? But because the sum of the Qn converges, then minus that sum also converges, and then the sum of the absolute values also converges. So when we put all this together, this means that the sum of the AN is convergent, which means that the original series is absolutely convergent, which we know was not, because we assumed it was conditionally convergent. Okay, so this cannot be. Now, the second case is also not possible. Let's do actually the second and the third at once. So you cannot have cases 2 or 3. So I will do 2, and you can do 3 for practice. Okay, remember case 2, the sum of the Pn converges, the sum of the Qn diverges. But in this case, what happens in this case? So we have a contradiction because we know that this one is convergent by hypothesis, the left-hand side. So therefore, if we want to write the sum of the Qn as the sum of the An minus the sum of the Pn, we would have a contradiction, because both of these are convergent, but the sum of the Qn is divergent. So this cannot be. And we have for case 3 is similar. So then that one cannot be either. And this actually proves that of all the 4 cases, only 4 is possible. Okay, so this finishes the proof of part 1 of the theorem. Okay, going back to the statement that said that both the sum of positive terms and the sum of negative terms are divergent series. And now we want to show part 2. Let's copy it here. And let's put here show 2, so that it's clear what we are doing. For any given number, any given real number S, there exists a rearrangement An prime such that S equals to the sum of that rearrangement. And that at first, this may look like magic because you could be like, okay, really any number? And yes, any number. And here the point, what Riemann realized, the very important point is that we have the two divergent series to play with. Okay, so the idea of the proof is that we are going to, whatever number we aim for, S, what we are going to do is to add positive terms until the first time that we pass that value S, and then start subtracting, okay, taking terms, negative terms in order until the first time that we fall below S. Okay, let me do it with a picture. So let's say we are aiming for this S here. So we are going to start adding terms until we pass. Once we pass, we start subtracting until we are below. Then we start adding again until we fall above. Subtract, add, and you see what happens here, that the series is going to start oscillating. The partial sums are going to be oscillating around S. Okay, and every time the oscillations will be smaller because the terms that are left will be smaller. Now that the idea is clear, we have to write it carefully. Okay, so let's take positive terms from the series, okay, and we are going to take just enough to exceed just enough to exceed S. Okay, so here let's say that we need n1 terms for that. So we have our A1, A2, well, actually let's put them as a sum, A3, and so on, and we make it all the way up to an plus 1, and this exceeds S, okay? And this is the first time that we exceed S. S could be a very large number, okay? In fact, it could even be infinity if we want. Now, here what we have is that the partial sum Sn1 is bigger than S. And we can always do this because we know that the sum of the positive terms is a divergent series. Okay, so just keep adding positive terms. Know for sure that at some point we will be above S. Now, what we are going to do once we exceed for the first time, we are going to start adding negative terms in order okay. Here actually what I wrote may look like they are all in sequence, but actually it will be more proper if I write primes to denote that I may be skipping negative terms, okay? So I'm writing the positive terms in order, but I'm skipping the negative for now. Now, when I start adding the negative terms in order, there will be, let's say, n2 terms until we fall below S again. Okay, what does this mean? This means that the partial sum is n1 plus n2, okay, of this rearrangement is going to be less than S. Okay, remember here we are rearranging the series. So I'm not, when I write S n1 plus n2, I don't mean the partial sum of the original series. I mean the partial sum of this rearranged series that we are constructing. Okay. And we can always do this. It doesn't matter how much down we need to go, because the series of negative terms is also divergent. We know that it's just a matter of time. This is the key point of Riemann's remark, the observation that we had two divergent series involved, and that was what was making this, what was puzzling everybody. And then we are below S, so we just need to repeat. We need to add positive terms in order until we exceed S again, say n3 terms. So we have S n1 plus n2 plus n3, 3 bigger than S, and so on. Okay. If we continue to repeat this process, adding each time just enough new positive terms to make the sum exceed S, and then just enough new negative terms to make the sum less than S, okay? What will happen is that we will get a convergent sequence, okay? These partial sums will differ from S by at most one positive or one negative term. This is because as we keep adding terms, there will be always a last term that was below S, and then when I add the next, I will be above. Okay, I will be either precisely S or I will be above. Okay, and then I will have to subtract again. Since the original series is convergent, that means that the AN go to 0. Okay, they are smaller as n goes to infinity. And that means that we can get the partial sums as close to S as we wish within any epsilon that we decide. Okay, just a matter of going out far enough in the series until all the remaining terms have absolute value less than epsilon itself. So then the partial sums converge to S, and that proves that the series that the rearrangement actually converges to the S that we decide. And that finishes the proof. Here, something that should be pointed out is that the rearrangement is not unique. Okay, the way we did is one way to do it, but there may be other ways. What we can do is to take, for example, let's say we want to take positive terms until we reach 100 or 100 billion. It doesn't matter, because we know that the sum of the negative terms is also divergent. So we can go very far away from the number S that we picked and be confident that we can bring the series back down to S. So we can do this in many different ways. That's why the rearrangements need not be unique. I mentioned it in the proof, but let's put it as a remark. We can also choose the target as infinity or negative infinity. We can decide that we can make the rearrangement diverge. Okay, how do we do this? Here, we only need to, for example, let's say we want the rearrangement to go to infinity. So we only need to pick positive terms, let's say, and reach 1,000,000, and then add one negative term. And then continue adding positive terms and reach 1,000,000,000. And then one more negative term. And then continue adding terms, reach a trillion. One more negative term. You see what is happening here? So it's going farther and farther out. So the partial sums, the sequence of partial sums is going to diverge, is going to go to infinity. And we can do the same for negative infinity. And finally, let me note that the theorem in the book is more general. So actually we could prove a more general version of what we just did with the same ideas. Okay, if we have, let's read together, if we have a conditionally convergent series, real series, given any two numbers, alpha, beta, that could be different or could be the same, okay, that's what we are saying here. Or they could be negative infinity or plus infinity. That's allowed too, okay. In that case, there exists a rearrangement with partial sums that have a lim inf alpha and lim sub beta. Okay, so this is a little more general. Before I was saying that the series would converge. Here I'm saying that there are subsequences that go to alpha and to beta respectively. Okay, and those could be, if they are the same, then we are back to the previous case. Okay, we have an equality here, alpha and beta, or they could be infinity or negative infinity. This is just a slightly more general version with the same idea for the proof.